Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
G'day everyone. Let me finish off a little bit about order statistics, which we have already covered the distribution of a single order statistic. So in case it wasn't clear last time, we talked about this. So the order statistics of variables x1, xn are, I will usually write them with this brackets notation. Oh. Again. Sorry about that. So we saw, okay, so what do? You get the n observations, and usually when we apply this they'll be IID, but for the definition of order of statistics they don't have to be IID. And the definition is you just write them in order from least to greatest. So if they're all unique, it's clear what that means. First the lowest one, then the second lowest, then the third lowest, and so on. If they're not all equally, they're not all different. In other words, if there are at least two that are the same, you have to include repeats. So if you have the numbers 2, 1, 3, 2, then your order statistics would be 1, 2, 2, 3. You have to have the same number of repeats. So if you like talking about a multi-set, which is just a set with counts, then that will I don't know why this is it. We'll repeat the same number. Okay, finally. No? No. Okay, finally. Let's do the multivariate distribution of order statistics. We've talked about univariate, and so to be clear, those are always in order from bottom to top. So I'll just say sorted ascending. And one thing that I wanted to be true in, now if they're not IID, this reasoning is not going to work because the multiplying of products will not going to work. So xi1 up to xn are IID. Now the order statistics are never going to be IID because they can't be independent. If one is always less than the other, then they're independent. So those, the derived order statistics will never be independent, but the underlying observations could be independent. So that's what we're going to assume, and that allows us with CDF I'll just write f subscript x. That's the same CDF of all of the x's. So so what is true in general, we said for the max, so the probability that the max is less than or equal to x, that's the same as all of them individually having to be less than x. So that's fx of x to the power n. We derived that before. And so if you want to differentiate that, if the derivative exists, in other words, if it's a continuous distribution, then you have the density of the maximum is, you would have to differentiate that, so n fx power n minus 1 times little fx of x. And by the way, that will match the definition we got by other means, which the other means were to say that just heuristically we want the maximum of all of them to exist at the point x on the real line. So there should be one that lives pretty much there. That's where the density comes from. And then you should have n minus 1 that are anywhere over here. And the factor of n comes from you have to choose which one of the 1 up to n is the one to be the maximum, and the others are over here. So there are n different ways to make that choice of which index is the index that achieves the maximum. So that's the density. Similarly, if continuous, that's the case. But this one will always be true. And then for the minimum, it's actually very similar. For the minimum, the CDF, except now we have to say it's the probability that the minimum of all the xi's is less than or equal to x. And so because minimum is hard to do with a product, like to say the minimum is less than or equal to x is to say at least one of x1, x2, x3 are less than or equal to x. And or is harder to do than and, because and we multiply the probability. So I don't want to do or. So that would be 1 minus the probability that minimum of the xi's is strictly greater than x. So that is equal to 1 minus the probability that x1, because of the independence, greater than x, probability x2 greater than x. See, they all have to be greater than x in order for the minimum to be greater than x. Probability that xn is greater than x. And that's equal to 1 minus f of x to the power n. So while you could expand that out, I think this is the simplest way in which you would never be able to write it. And so the consequence is if the density exists, so if it's continuous random variable, which it might not, then the density little f for the minimum is, once again, I just have to differentiate this. I get a minus n. So there's still an n, there's still the derivative, which is, there's a minus from here and there's a minus in the minus fx of x. And then I get this to the power n minus 1. 1 minus fx of x to the power n minus 1. So that's a full derivation in the case of the minimum or the maximum. And I gave you this formula last time for any k that you might choose between 1k and n. The density of the kth choice is equal to I have to do, there's a constant which I'll write later. There's all the ones that have to be less than the k, less than xk, they're a k minus 1. Because if you think about it on the number line, once you're asking x to be the kth observation, you're expecting there to be k. So in the later case, you're expecting there to be, I mean, when we did that, we were talking about us having n minus 1 values all over here and 0 values over here. But in this case, we're asking to have k minus 1 values to the left of x and n minus k values to the right of x. So we expect to have chance of being less than x to the power k minus 1 times density at x times chance of being greater than x, which is 1 minus f of x to the power n minus k. That's the chance of being greater than x. Then I have to multiply by the number of different ways of choosing which guy goes in kth place, which is actually n factorial divided by k minus 1 factorial n minus k factorial. Okay? That's because you can permute the ones to the left of xk that many times, and you can permute the ones to the right of xk that many times. Okay, that's the density of a single observation. You can also do joint density. And joint density is important because they're not independent, as I said. For instance, the minimum and the maximum are not independent. One's always less than the other. In fact, the ith observation will always be less than the I plus 1 observation. But the joint density can be written down. You just think about having them on a line. Let's say I want x to be here and y to be here, and I want that to be the kth observation. Or let's say I want x to be the jth observation and y to be the kth observation. So, in other words, we're talking about joint density of xj with xk. Okay? So those are now considered as a pair. Now, of course, we'll assume, if we assume j less than k, then clearly this is a density that is only supported on variables little x less than little y, or less than or equal to, but it turns out because they're continuous, the probability of being exactly the same is 0. So I'll just say it's supported on x less than y. And what is that density? xj and xk together. Well, you have to have, evaluated at x comma y. You have to have x less than y for this to be valid, otherwise you'll get 0. And if that's the case, you have the density at x itself, you have the density at y itself, and everywhere that I've been writing f, I mean f subscript x. Oh, okay. I don't want to write that every time, so I'll just remind you that f is shorthand for the density of the individual for the CDF of the individual observations, and little f is the PDF of the individual observations. And I'm only doing the continuous case. X continuous only. So the only case where I said anything definitive about the non-continuous case is for minimums and maximums. That's kind of less interesting. So I'm going to have that one there, and then how many observations are going to have to be to the left of x? Well, that's j minus 1. So that's f of x to the power j minus 1. And then how many observations are going to have to be between x and y? That's k minus j minus 1. Like if I have between the third and the fifth observation, there's 5 minus 3 minus 1. Because, you know, it's going from the k minus 1 down to the j. So, and then what's the probability of lying between x and y? It's capital F of y minus capital F of x to the power k minus j minus 1. Okay? And then I have to have 1 minus f of y is the larger of the two, to the power n minus k. That's because there are n observations total. So how many there have to be n minus k observations over here, k minus j minus 1 here, and j minus 1. So if you check j minus 1 plus k minus j minus 1 plus 1 plus n minus k, they all add up to n. So, and then there is a constant out the front. Okay, so just to reiterate, x has to be less than y for this to be non-zero. And the constant out the front, let's call it c, j, k, n, just because I don't quite have space to fit it there. The constant, we've put all the densities and all the probabilities. The remaining factor is how many different ways are there to choose which one is in kth position, which one is in jth position, and then which are the ones in these positions. So if you think about it, that's amounting to coming up with a permutation of all the numbers 1 up to n. That's having all of them in order. And then, but I don't care which order the ones to the left of x are in, so I divide by j minus 1 factorial. I also don't care which order the ones between x and y are in, so that would be k minus j minus 1 factorial. And I also don't care which order the ones to the right of y are in. And so that means that one will be n minus k factorial. So that's the way it is. You can also write this as a multinomial coefficient once again. I have n objects and I have to divide them into 5 categories. The 5 categories are to the left of x, x itself, of which there's only one, between x and y, y itself, of which there's only one, and then to the right of y. So there's 5 categories and the respective counts in each category. J minus 1, 1, k minus... something like... oh, the light went off. K minus j minus 1, and then 1 in the 4th category, and the last category is n minus k. So that is a rather large multinomial coefficient. Okay, so that's the joint density. Now, I'll just say dot, dot, dot. It's not that interesting, but if you really wanted, you could do a joint density of 3 of them. That's, you know, you'd have something very similar or expand. Let me just do the last one that is of interest, because you could do 3 with a similar pattern. It'd just get very, very complicated and not so interesting. But let's say the joint density of all n order statistics. Because there's no reason not to consider an n-dimensional distribution. It's, now, it's a random point in n-dimensional space, and it'll have the property that the coordinates are in increasing order. And once again, they certainly won't be independent because they're in increasing order. If you wanted the joint density of the original ones, rather than just the order statistics, of course you just multiply all the individual densities for independence. Here we can't do that because they're not independent, but what we can do is follow the same pattern. In this context, you're thinking about very specific desired values, x1, x2, x3, all the way up to xn. So these are very specific desired values, and there's nothing in, I'll just remark, by the time we found all n order statistics, there's nothing in the gaps. So I don't have to worry about any of the ones that are in the gaps. So that's quite easy in that case. The joint density of all the order statistics evaluated at the point x1 up to xn. So it's just, first of all, I have to have f of x1, f of x2. This is the density at each of those points, f of xn. Because they're continuous, there's no chance that they land on top of one another, 0 chance. And this is only going to be supported, I'm not finished yet because there's a constant, it's only going to be supported on points where x1 is less than x2, less than all the way up to xn, because there's 0 chance of the order statistics not being in order. Yeah. So finally, we have to get the constant right, and that's just a matter of thinking. By the way, this looks awfully similar to the independent case. The independent case, you'll just multiply all those densities. So the only thing that stops it being independent is this restriction. Remember, it's not, if the domain is not, you know, a generalized rectangle, so like the same in every, if the domain of x doesn't depend on the other xi's, if it's independent, the domain of x can't depend on the other xi's, and so this one is clearly not independent. But we've actually, if you think about it, we've sort of removed a large fraction of the space by insisting on that. Only in 1 over n factorial cases of the ordering, if you think about all the different orderings you could have, only 1 out of those n factorial orderings is in the correct order from bottom to top. So that's actually n factorial times this. Another way to see that is that this is the multinomial coefficient where you have n choose 1, 1, 1, 1, 1, 1, 1. Right? N, that would be n factorial divided by a whole product of 1 factorials. It's just n factorial. So that's kind of a nice joint formula for the joint distribution of n variables. So let's, I can do an example. Let's do joint distribution of okay, x1, x2, x3, if I just do a 3-variable case where the xi's are iid exponential 1, this is an easy case because the density of each of those xi's is e to the minus x, where x is positive. So that will still have to be reflected in the final solution, x1, comma x2, comma x3. Now we can just write this down. There are 3 factorial ways to arrange them, multiplied by e to the minus x1. Okay, so this is evaluated x1, x2, x3. E to the minus x2, e to the minus x3, and we have to put the constraint on it. X1 is less than x2 is less than x3. But in addition, because of this constraint that was on the original density, all of those have to be positive. So a simpler way of running that is 6 e to the minus x1 plus x2 plus x3, once again on the proviso 0 less than x1 less than x2 less than x3. So that's just an example of what you do with order statistics. Okay, I want to wrap up talking about order statistics now. That's pretty much all there is to know about them. And let's go on to talking about more normal theory. So this is really chapter 7, more on, you might not think it was possible, normal random variables. But particularly this is going to cover why they're important in arising from natural situations, which is more or less the central limit theorem, and also what to do once you have a normal sample. So I'll even say normal samples. Okay. A sample is, as the name suggests, it's something coming from an experiment, and we'll focus on the case of IID experiments where the outcomes are normal. And then when you want to do inference, it's really important to understand how the properties of that sample relate to the underlying distribution. So that's what we'll do. And the first thing to do here is let's okay, yeah, I could do this in either order, but why are normal variables important? Okay, so there are probably, we've seen a number of reasons for this already, including, we saw heuristically that they arise when you take a limit of binomials, and I even gave a proof of that quickly in the case, sort of by bare hands, in the case where you had binomial 2n comma a half. So that's non-examinable, but that was just one way that we saw where the normal density function comes out from. So the next, in the most general case, the central limit theorem tells you that you'll get a normal limit even for much more general variables than binomials, and much more general than, I think we tried a negative binomial on R and we saw that it also had a normal looking shape, and many other, in the case of large K or large N. But it turns out whenever you're averaging a large number of any IID random variables, you get a normal with one proviso, and that is the proviso that you have to have, the variable has to have a variance. It has to have a finite second moment. So let's say the central limit theorem, and I'll just state it here. If there are many generalizations of this, but this is the most basic case. If x1, x2 all the way up to x, well, I'm just going to treat it as an infinite sequence. I'm going to be taking averages of the first n of it, but then I'm going to be letting n to go to infinity. So I may as well take an infinite sequence. Are all, but they all have to be mutually independent. Normal, no, not normal. IID random variables. So they all have the same CDF. If you want, you could write that CDF, but I won't. Such that the key thing is that I'll write it this way: expected value of xi squared is finite. Okay, so that's the quickest way of saying they have a second moment or they have a variance. So, and whenever they have a variance, they must also have a mean. And expected value mu and a variance sigma squared. And it's a common expected value to all of them, common variance to all of them, and that variance is finite. Okay. So there's a finite real mean and a finite real variance. Then, so it's easy to figure out what the object of interest is the sample mean, x bar, which is x1 plus x2 plus just the arithmetic mean. xn divided by n. Now, normally that would be a satisfactory notation, except in this case I want to call it x bar subscript n, and that's because I'll be considering different means with different number of variables, and I'll be saying what happens in the limit. So often I write it without the subscript, but here I'll write it with the subscript. Let's say this tends to so I'm going to put a brackets d here for, this is a form of convergence that we haven't talked about before, but that d means in distribution. So what I'm not saying is that the actual random variable converges to, and I'm also not going to, okay. Before I make it converge, I have to talk about, okay, so if xn bar is that sample mean, then I have to do xn bar, I have to standardize it first, because the sample mean will actually get closer and closer to the true mean as n gets large. That's the law of large numbers. So in order to expand that out to something that won't have a trivial limit that's just a single point, I have to subtract the mean and divide by the variance. So that's what we do. Standardization is to subtract the mean. So because xi's all have expected value mu, that means xn bar also has expected value mu. And because the xi's all have variance sigma squared, that means the sum of n of them has variance n sigma squared. N sigma squared, because you add variances of independent variables. And on the bottom you have, that'll give you an over n squared. So the actual variance of xn bar is sigma squared over n. And not only that, if you divide by the standard deviation, sigma over square root n, that converges in distribution. So I'll write it in words. In distribution to normal 0, 1. Okay, so that is what the central limit theorem says. And it's actually very, the reason this is maybe a hard theorem or a very comprehensive theorem is because it assumes very little on the distribution. You do have to have a finite first moment and a finite second moment. But for instance, I haven't assumed that it's continuous. I haven't assumed that it's discrete. I haven't assumed, it could cover many other cases even than that, a mixture of continuous or discrete. So I can't assume that there is a variant, I can't assume that there is a density function that I can use or a probability mass function. So that inevitably means that the proof of this is a little abstract, and it's not going to be examinable. So, but I will do it. Let me just do a proof sketch and emphasize that this is not examinable. We already talked about the binomial case, but it's probably too much of a stretch to imagine just because it's true for binomials with p equals a half that it's true for everything. So why does this come out? This is kind of a nice application of MGFs. So first I'll talk about a fact about MGFs. Okay, so the fact about MGFs says if you've got a sequence of random variables, I'm not going to use xi's because I've already used those. So let's use v1, v2, v3, ... are random variables where, so we have to check that the MGFs converge. And because MGFs might not always exist, particularly for instance, by the way, an example of this are exponential or gamma random variables, are variables that have a mean and have a variance. We've calculated that. But they don't actually have an MGF existing everywhere. They only have an MGF near the origin. So, and unfortunately, it'll turn out that MGFs are not quite general enough to cover all these cases. So I'll mention that a little bit at the end. So if these are random variables where the MGF, MV1 or MV n of t. So each of them has a moment generating function, and it tends to some m of t. So that's as n tends to infinity. And then for what t is this true? For all t near 0. It doesn't have to be true for large t, because it might not even exist for large t, but just for some neighbourhood of the origin, then this always converges to m of t. And where m of t is the MGF of a distribution, what shall I call the distribution? Okay. We haven't really used notations for distributions much, so I'll just call it nu, some kind of Greek letter that we don't use very much. That looks a lot like a V, but it's a Greek letter nu. Okay, so in this example, it's going to be normal 0, 1, but I'll just write nu because that's a general distribution. Then this is what I was claiming to be true. Vn of t tends in distribution, so D is it short for convergence in distribution, to nu. Okay, so if you can prove that the MGFs converge, then the underlying distributions converge. Now, some of you might be wondering what in distribution means. In this context, it means the cumulative distribution function converges. So that would be CDF. So you can say that this variable converges in distribution to normal 0, 1 if the CDF converges to capital phi. We talked about capital phi before, which is just the standard cumulative distribution function of the normal. Okay, so that's the statement of the theorem. Now, this so because this is only a sketch, I'm not going to go into all the byways of how you get around here. So let's assume that the individual variables, we don't know what distribution they have, but let's assume they have a moment generating function exists near 0, so in a neighbourhood of 0. Okay? Then, so I now need to find the moment generating function of xn bar of t. Well, let's first so that's the expected value of e to the power t times xn bar, so x1 plus x2 plus dot dot dot. So this is much like doing the MGF of a sum, which we talked about before, except this time it's the sum divided by n. So that's going to be equal to expected value of e to the power t over n times x1, and then because of independence, you do a product again, e to the power t over n x2 dot 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 expected e to the power t over n xn. Okay, and so for all t for which this exists, that will be that, and I can write that as a product of the corresponding MGFs, mx of t over n. So that's what the first factor is. But that's mx1. But remember, all the xi's are the same. So I'm just going to write this mx of t. Remember that all the xi's have the same distribution. So the moment generating function is the same for all of those. And so I'm just going to call that mx of t. mx of t over n to the power n. Okay? And then, so now I have to do, I think I better name this so I don't have to write it all out. Zn will be my standardized version of xn. Z is often a letter used for standardized versions because mean 0 and variance 1. So moment generating function of Zn of t is going to be equal to mx of t over n to the power let's just so that is m x n bar minus mu divided by sigma divided by root n of t. Okay, so the first thing is there's a constant in here, e to the minus mu t divided by sigma divided by root n. Okay, that's because of this constant term here. And then I have to do mx of t over n, but then I have to divide that by sigma divided by sigma divided by root n. Okay. So that's what mzn of t is. So, okay, so maybe the key thing that we have to do is we have to use Taylor series for mx. Now, why is there a Taylor series of mx? Well, because we know there is a mean and there is a variance, and we know that moment generating functions expand out to give you the mean and the variance. So it's 1 plus mu is known to be the mean of x, so mu t plus sigma squared. By the way, it's actually, you remember what goes in the moment generating function is actually the raw moments, not the centered moments. So the first raw moment is mu. The second raw moment is ex squared, which is actually sigma squared plus mu squared. Remember that ex squared is mean squared plus variance. Yep. So I have that Taylor series, and so because I know it exists around 0, that's a perfectly good thing to substitute in. And the one thing that I forgot to do is that this is all to the power n, because mxn of t was to the power n. So okay, if you substitute in the Taylor series and cancel out a little bit involving the means and the variances, maybe I'll jump to the end. It will be e to the power 1/2 t squared. So there's quite a bit of algebra when you substitute in those Taylor series. Plus, there will be, let me write it this way, order of t cubed. Okay, so something no bigger than a constant times t cubed. Then if you plug that in there, you'll get order of 1 over square root n in here. So the half t squared doesn't depend on n, and then the remaining terms will be things that vanish to 0 as n tends to infinity. So mzn of t converges near 0 to e to the 1/2 t squared for t near 0. And that means that Zn converges in distribution to normal 0, 1, because we know we've calculated the MGF. So that's, okay, there are obviously a couple of things I didn't prove, including this fact about MGFs, and I didn't do the full algebra here. But that is a proof in the case where it works. And unfortunately, there's one final wrinkle if you want the absolute full story. The final wrinkle is the MGF. I said let's assume that it exists near 0. Unfortunately, it's the case that some variables that have a variance still don't have an MGF. We don't have an example of that yet, because the one example we gave of heavy tails was Cauchy. But Cauchy is a variable that doesn't even have variance. Nevertheless, it's a fact there are ones that have variance but don't have an MGF. One of the examples is a T, like a T3 or T4. We'll get to T distributions soon. So unfortunately, this assumption was not always valid. So I'll just, this belongs in a more advanced course. So if no MGF, okay, so some variables don't have an MGF, you use the so-called characteristic function. And the reason that we're not, once again, this proof is not examinable, and one of the reasons for characteristic function is that gets around the MGF not existing by using complex numbers. So instead of expected value e to the tx, you do expected value e to the I tx. Now it turns out that this really has kind of essentially the same properties as the MGF, but it works in all cases, because when you do expected value e to the I tx, that's a complex value of norm 1, complex number of norm 1. So the expected value always exists, it's bounded. So that's just even slightly, so you have to use complex numbers to do that. Otherwise the proof works the same way, the same Taylor series expansion of the characteristic function, all the rest of it. As far as the remainder of that, I'll just leave it to a more advanced course. But essentially, you have to go via some of these characterizing functions. And for those of you who've done some maths or will be going on to do things like ordinary differential equations or just higher calculus courses, it's worth knowing that the moment generating function is effectively the same as the Laplace transform of the measure. You may hear a lot about Laplace transforms, which are effectively Laplace transform of a function. You integrate e to the minus tx f of x. So this is effectively the same if you take expected e to the tx. It's a Laplace except with a minus sign in the wrong spot. Similarly, a characteristic function is just the Fourier transform of the density with minus instead of a plus. So characteristic functions are Fourier transforms. Moment generating functions are Laplace transforms, and there's a whole body of theory that allows you to invert Fourier transforms and invert Laplace transforms. So once you've studied that and you've seen how to invert them, you'll effectively know why this fact is true. That if the Laplace transforms of a function tend to something, then the original functions tend to that thing. And same for Fourier transforms. Okay, so that's all I'm going to say about that proof sketch. We now have the central limit theorem, and I'm going to take that as a pretty good justification of the importance of normals, because even if you have things that are not even normal, not even vaguely, this covers all sorts of things. You could have a bimodal thing, just like a Bernoulli variable, or something with multiple, things. And it can even be quite skewed, just so long as the variance is finite. You might wonder, how does that work if it's extremely skewed? Well, the central limit theorem states something about the n to infinity limit. It doesn't say anything about how quickly it converges. And it turns out, with a very skewed distribution of xi's, the convergence will be slow. That actually turns up in practice when we do inference, because people say, let's just use a normal approximation for something for inference. Well, it turns out it's all a matter of how big does n have to be before you have a normal approximation. We usually say, if n is bigger than 30 or so, just use a normal approximation. Turns out, if the underlying distribution is very skewed, n has to be a lot bigger than 30 before it's a reasonable approximation. So that's kind of the reason. There is a good rule of thumb in the binomial case, which is like, expected number of successes is at least 10. You probably remember that from first semester, or expected number of successes at least 10 and expected number of failures at least 10. That's the reason for those criteria. You want the central limit theorem to have kicked in. Okay, so let's now look at the big theorem about normal IID normal samples. Okay. So unlike in the CLT case, because CLT is very important, but CLT applies to variables that are IID but are not normal. Okay, so if you're not normal, you don't have the magic properties of normal that we've talked about. For instance, correlation 0 does not imply independence if you're not normal, so you don't have those good properties. So we're now going to just kind of assume that you're in the normal case, and we'll have the best results there, and then we'll later relax that a little bit. So here's the big theorem. It has three parts. So x1 to xn are IID. So now I'm assuming that they are normal with mean mu and variance sigma squared. And now I'm just going to give you the notation. Of course, x bar, I'm going to drop the subscript n because I'm not letting n tend to infinity. X bar is x1 plus ... plus xn over n. So that's the sample mean, as you would recall. And let's also have the sample variance, which we usually call s squared, unless there's a reason to make it more complicated. So on the definition, that is 1 over n minus 1, sum I equals 1 to n of xi minus x bar squared. So x bar defined as that. So this is, of course, called the sample variance. Okay. Then, three things are true. X bar has a distribution normal, mean mu variance sigma squared over n. So that's not hard because we know that linear combinations of normal are normal, and it's easy to calculate the variance and the mean. Second statement is that S squared. S squared is essentially a chi-squared distribution, but unfortunately it's only an exact chi-squared if you get rid of the n minus 1 denominator that you just put in, and you also have to divide by sigma squared. Sigma squared is, remember that I didn't assume they were standard normal. There's a variance involved, so if I want to convert it to standard normal, I'd better divide by the sigma squared. So that one has a distribution that is chi-squared with a certain number of degrees of freedom, n minus 1. Now, we did talk about chi-squared before, but just as a refresher, that means you get n minus 1 independent standard normals, square them, and add them up. And what are the normals that go into that? They're not the xi's. They're definitely not the xi's, and the very important reason that they can't possibly be the xi's is because the most interesting part of this is that you have independence. Now, I stress that this is true only if your sample is actually normal. If your sample was something else, like in the central limit theorem, IID, but not normal, then the sample mean and the sample variance are not likely to be truly independent. They might be kind of approximately independent, but not truly independent. They're only going to be truly independent if the inputs are exactly normal. Okay? So that's maybe the most important part of the theorem. So So although maybe part 3 is the most surprising part of the theorem, it's actually quite easy to do. It's 2 that's the harder thing to prove exactly. And let's, okay. So now we're in the realm of things that are a little bit easier to prove. So I will actually give you the proof. So for part 1, as I said, linear combinations of IID normal are normal. Okay. So we know it's normal, we just need to calculate the expected value of x bar is equal to n times expected value of n times mu divided by n, which is mu. So that's an easy calculation. The expected value of s squared is going to be 1 over n minus 1 sum I equals 1 to n. So this is a bit, I do have to calculate this a little bit, xi minus x bar squared. Right? Because so of course these ones are not independent, but I don't have to have independence in order to break up an expectation of a sum of expectation. Just remember that linearity of expectation is regardless of whether they are independent or not independent. Okay, but then so that's 1 over n minus 1. I actually have to calculate the expectation of this. There'd be a number of ways to do that. It's going to be maybe, you could make it easier by doing funny algebra, but I'll just do it by brute force. So there's still the sum I equals 1 to n of expected xi squared minus expected value of xi x bar. Now don't get into the trap of assuming that x bar can be taken out the front because it's the mean. It's the sample mean, but that is a random variable, so it still needs to be taken into account. So sorry, that's minus 2 plus expected value of x bar squared. Okay, so I'm sure there would have been a quicker way to do this, but you can just evaluate this. Sum I equals 1 to n of let's say this is mu squared plus sigma squared. Remember, it's just a second moment. Minus 2 times, the only one that matters here, x bar, if you look at the definition of x bar, it has every variable, which are all independent, divided by n. So that's minus 2 divided by n times expected value of xi, which is mu squared plus okay. Sorry, I'm not actually... Yeah, okay. Where I went wrong when I did this was I expanded it out in terms of expectation, which is not quite as nice in the case where the mean is not 0. So I'm going to write this another way. Expected value of s squared is 1 over n minus 1. Sum I equals 1 to n. The variance of xi minus x bar. This is going to make it a lot better in my calculations. That's because expected value of something squared is the same as the variance of that thing in the case where the mean is 0. We know that expected value of xi is mu, and we know that expected value of x bar is mu. So this thing I'm taking the square of has expectation 0. So this is a much nicer way to write it. So that's 1 over n minus 1 sum I equals 1 to n. And now I just expand that out. Variance of x